Let's go ahead and take a look at our first example. Let's assume that we're having to multiply x to the third power times x to the second power. Well, my first question is, what does this really mean? And x to the third power literally means I have three x's multiplied together. Times x to the second power means I have two x's multiplied together. So, if I have three x's multiplied together times two more x's multiplied together, that gives me a grand total of 5 x's multiplied together, or x to the fifth. So in this case, I literally want you to think of this as 3 x's multiplied together times 2 more x's multiplied together gives us a total of 5 x's multiplied together. So we literally just add our exponents. 3 plus 2 is 5. Let's take a look at our second example, which is division. I literally have x to the fifth divided by x to the third. If I write this out, that literally means 5 x's multiplied together on the top times 3 more x's multiplied together on the bottom. So let's take a look. I've just basically recopied it. And what I basically do if I have a fraction is I simply cancel, which leaves me with 2 x's. So in this case, I literally have x squared left over. So if I had 5 x's on the top and I canceled 3 of them, that left me with 2 x's on the bottom. Let's now take a look at our third example. In this case, I have x to the second power, but I'm raising that to the third power. What does this really mean? Well, once again, what it means is that I have 3 of these x squareds multiplied together. So I want you to literally look at that as 3 sets of 2. And of course, once again, it's all multiplication. Each one of these x squareds literally means I have 2 x's multiplied together times 2 more x's multiplied together times 2 more x's. All of that's all multiplied together. So I have 3 sets of 2 multiplied together, which means I have, and I should have written it down and I didn't, 6 x's all multiplied together. So basically the rule of thumb this time is 2 times 3 is 6. Let's take a look at our fourth example where I'm actually going to do this process in reverse. I have x to the second to the third power equals x to the sixth. So let's consider how you would find the third root of x to the sixth. It's a very similar rule, pretty much the reverse of what we just did, but let's take a look at it. My real question is, what number multiplied times itself 3 times yields x to the sixth power? Well, basically what we're saying in this case is that if I had x to the second times x to the second again times another x to the second, pretty much what I just had up above, if you'll recall. What I get if I multiply 2 x's times 2 more x's times 2 more x's is basically x to the sixth power. So in this case, what's really happening is this. When I take the third root of x to the sixth, I'm really saying to divide those 6 x's into 3 groups. So literally you can just take your power, 6, divided by your root 3, and that equals x to the second. 6 divided by 3 equals 2. Now, I want you to notice here how I've written this exponent as a fraction. Remember, fractions really are division. Just remember that it's the power on the top and the root on the bottom. Let's look at some actual problems that apply these principles we just learned. Our first example here, we're going to take 4 to the 3/2 power. Now remember, just a little while ago, you can even rewind if you need to see it again, we learned that this is always the power divided by the root. So 3 is my power and 2 is my root. Now the way I've written it this time, I'll take the third power first and then I'll take the second root. Now, I could also do that the other way around. I could take the second or square root first and then take the third or the cube. Well, let's take a look here. If I do it this way, I have 4 to the third power. That's 64. Again, I want you to notice that 2 is understood there. It's understood to be a square root if I don't write anything else. And of course the square root of 64 is 8, since 8 times 8 is 64. Now let's take a look at this one. If I take the square root of 4, the square root of 4 is 2. And then if I apply the cube, 2 cubed, or 2 to the third power, is 8. So once again, it really doesn't matter which way you work it out. You can use any of these rules in any order you want, at any time you want, and it should work out. You do what makes sense to you. Let's take a look at another example. Let's talk about the square root of x. And I still want to concentrate on that same formula that I was using. Now, I want you to notice that there's an understood 1 and an understood 2 here. So this is understood to be x to the 1 power and the second root. I've merely filled in the digits, if you will, that were understood. And if I now convert that to exponential form, again, it's power over root, or 1 over 2. So in other words, the square root of x is actually equal to x to the 1/2 power. Let's take a look at another problem, and another principle, frankly. What if we had 4 to the 0 power? What would that equal? Well, what we're saying is that I have no 4's all multiplied together. In other words, I've got nothing. Well, what is nothing when you're multiplying? How could I even end up with 4 to the 0 power? Well, let's think about the fraction. 4 to the second power over 4 to what power would leave me with 4 to the 0 in the first place? Well, obviously, 2 minus what would leave you with nothing? And the answer is 2. So I'd literally have to have the same thing top and bottom in order for them to leave me with none. Specifically, 4 to the 0 would then equal 4 times 4 over 4 times 4, or 16 over 16. And of course, 16 divided by 16 is 1. You could also think of this, however, as I'm just going to cancel out all my 4's. They all cancel, so I'm left with nothing. And the question I'll ask again is, when you're multiplying and you've got nothing, what do you have? So take a look here. I've multiplied 4 times nothing. I've left the blank empty. And I still have 4 because it does nothing. Well, what does nothing when you multiply? And the answer is 1. And that's because 1 is the multiplicative identity. Let's look at another example. What if I had 4 to a negative power? What would 4 to the negative 3 equal? Well, again, let's take a look here. I've got 4 to the second power over 4 to what could even result in having a negative number of 4's to begin with. What number, in other words, would have to be in the denominator to have this result be 4 to the negative 3 power? Well, the point is, 2 minus what number would give me negative 3? Now, I just picked the 2 at random, to be honest, but no matter what number I picked here, if I'm going to end up with negative 3 when I subtract, I have to make certain that the number on bottom is 3 bigger. So in this case, 4 to the 5th. So in this case, what I had was this. I have 2 4's in the top, I have the 5 4's I have in the bottom, and again, I could cancel out, right? Actually, these should be 4's, not x's, I just realized. So I'd be left with the 3 extra 4's in the bottom, which, of course, could be just simply written as 4 to the third power. So notice there was nothing left in the top. I canceled all those 4's out, and since there's nothing there, remember, when you're multiplying and you've got nothing, you've got a 1. That principle is going to come up a lot. You just put that in the back pocket for a while, because it's going to come up not only in this class, but in a lot of other applications you do in mathematics in the future. So, if you have a negative exponent, the simple rule of thumb is you move it to the bottom. By the way, the opposite is true as well. If the negative were in the bottom, you just move it to the top and make it a positive. So if you have a negative exponent, rule of thumb, you move it. Wherever it is, you move it to the opposite location. And then, of course, you change the sign to a power, to a positive power. Let's take a look at another example. What if I have something more complicated than just one variable or one number inside my parenthesis? What if I'm going to square x to the third times x to the second times y to the third. What do I get if I raise that to the second power? Well, what I'm literally saying is I have 2 of that parentheses multiplied times each other. Now, you need to notice as well that this needs to be multiplication, or frankly even division, inside the parentheses for this principle to apply. In this case, I've got all multiplication, so I can simply rewrite this without the parentheses. That's just x squared times y cubed times x squared times y cubed. And since I have multiplication, and of course 2 times 3 is the same as 3 times 2, right? I can reorder these any way I want. So let's put the x's together. So I just take these 2 guys and put them beside each other. And then I did the same thing with the y's and put them together. So what I have now is x squared times x squared. And on this side I have y cubed times y cubed. And when I combine those, basically what I'm saying is I've got x squared squared, and I've got y cubed squared as well, or 2 of each of those multiplied times each other. And then of course that leaves me with 4 x's altogether times 6 y's. Now the rule of thumb is this: as long as this is all multiplication and division inside this first parenthesis, I apply that same principle we learned way back on what? I think it was page 3. 2 times 2 is 4. And by the same token, 3 times 2 is 6. So again, if you have a power to a power, and it's all multiplication and division on the inside, you can just distribute that power all the way through the parentheses. What if I have a root? Does the same thing apply? Well, of course, you remember from class that, and we'll look at it here down the line, that powers and roots are the same thing. It's just 2 sides of the same coin, frankly. So if I have something like the square root of 9 times the square root of 16, is that equal to the square root of 9 times the square root of 16? This is pretty easy to verify. 9 times 16 is 144. The square root of 9 is 3. The square root of 16 is 4. And of course, the square root of 144 is 12, as is 3 times 4. So once again, just like I did with the power, I can distribute the root to every single number or variable or whatever item it is in the parentheses. And remember, you can only do this as long as you've got multiplication or division inside that radical. What if you don't have the same radical? What the heck do you do then? Well, look at this one. I have the square root of x, and there's an understood 2 here, of course, times the cube root of x. Well, if they were the same, I could frankly just apply the same property that I used the last time in reverse. But this time they're not the same root, so I can't simply pair them together somehow. What I have to do is this. We're going to go ahead and convert these to fractional powers. Now, the tricks that I'm going to show you here, or the rules that I'm going to show you, frankly, could be applied in root form, and once you get good at this, you could probably get away with doing that. But in all my examples that I show you here, I will actually use the fractional form. First of all, notice the first one. There's an understood 1 and an understood 2. So this is automatically power over root, or x to the 1/2 power. For the same reason, this would be x to the 1/3 power. Now remember what you do when you multiply? You have to add your exponents. Well, I can't add a 1/2 and a 1/3, so what do I have to do? I have to come up with a common denominator, which would be 6. Multiplying top and bottom by 3 would give me 3/6, which is equivalent, of course, to 1/2. 2/6, multiplying top and bottom by 2, is equivalent to 1/3. Well, now I can add them. 3/6 plus 2/6 is 5/6. And now, frankly, I can put it right back into radical form because this is the root and this is the power. When you see this, I want you to start thinking of it as the 6th root of x to the 5th power. And we're done. So how about a division problem? What if I have 6 to the 3rd root divided by 6 to the 2nd root? Well, I'm going to repeat pretty much the same process here, and I'm going to do it a little more quickly, I think. That would be 6 to the 1/3 power divided by 6 to the 1/2 power. Now I need to subtract my exponents, but I need a common denominator, so once again, the 1/3 becomes 2/6, and the 1/2 becomes 3/6. Now, I need to subtract my powers. 2/6 minus 3/6 gives me a negative 1/6. Now, oftentimes you're going to be asked not to have negative exponents. Do you remember what to do in this case? If you have a negative exponent, you merely need to move it. Well, I don't have a fraction, so first of all, I'm going to make a fraction. This is in the top. What number would be in the bottom? Because there's nothing there. And of course, when you're multiplying and dividing and you got nothing, you've got a 1. Don't forget that. That's always going to work. So at any rate, I now merely need to take this and move it down to the denominator to make this correct. When I move that to the denominator, it becomes 6 to the positive 1/6. And of course, that leaves me nothing in the top. So once again, what number has to go there? Just a few more, I promise, because the cinematographer and love of my life is already yawning and complaining about tired arms from holding up the camera. So here we go. First of all, let's define what we mean by the square root of 2. What is a square root? Well, a square root is the number you take times itself to get that number. So by definition, the square root of 2 would be the number you take times itself to get 2. So therefore, what does the square root of 2 times the square root of 2 equal? By definition, the square root of 2 is the number you take times itself to equal 2. So how about the cube root of 2? Well, the cube root of 2, very similarly, would be the number you would have to multiply together 3 times to get a 2. So what would that number be? Whatever the cube root of 2 is, when you multiply it by itself and multiply it by itself again. In other words, it's the number I take times itself 3 times to equal 2. Now, let's use that little nugget of knowledge to simplify the square root of 8. Let's take a peek here. What is the square root of 8? Well, first of all, 8 is the square root of 2 times the square root of 2 times the square root of 2. Or more properly, 8 is 2 times 2 times 2. So the square root of 8 is the square root of 2 times 2 times 2. But remember, before we distributed the square root across everything, I'm more or less going to do the same thing now. I can think of that this way. By the way, you can also obviously undistribute if you want to think of it that way and collect these terms together. So if you have the square root of 2 times the square root of 2 times the square root of 2, that's also the square root of 2 times 2 times 2, or 8. You can either put these numbers together or take them apart as long as the radical is the same. But remember now, that wasn't really our point on this problem. We're just trying to simplify the square root of 8. The key to this problem, well, what is the square root of 2 times the square root of 2? Do you remember? By definition, when you take that number times itself, you get 2. And of course, I have that square root of 2 left over. So the answer to my problem is very simply just 2 radical 2. You don't, of course, need to write the multiplication sign. I've just done that for emphasis. Let's do a couple problems now to end up where we rationalize the denominator. In this problem, we have 2 over the square root of 6. Basically, rationalize means make that into a rational number, which is a square root is not, frankly. We've got to get rid of the square root. So when you read that, basically you need to almost think of it saying, get rid of the square root. Well, remember, we can multiply top and bottom of any fraction by the same number, because if I have the same number top and bottom, it equals 1, which of course is nothing, and it doesn't do anything to my number. Well, what can I multiply the square root of 6 by that will eliminate that radical? Well, there's many choices, but frankly, the easy one is to multiply it by itself. So I'm going to simply multiply by the square root of 6 over the square root of 6. Again, please remember that the value of this number is actually 1. So I'm taking 2 over the square root of 6 times 1, which changes nothing because 1 is nothing when you multiply, remember? On the bottom, it's easy. The square root of 6 times the square root of 6, well, it's by definition the number you take times itself. If you take it times itself, you of course get 6. The top is even easier. 2 times the square root of 6 is, well, frankly, 2 times the square root of 6. There's not a whole lot you can do there. If you stop here, though, you're going to lose half credit on the test, because remember, one of the things I'm going to always want you to do is to reduce your fraction. And do you see this? 2 and 6 reduce. So in this case, frankly, you reduce that to a 1 and a 3, or a 1/3. You'll notice I put the 3 on the bottom, but the 1's understood because, again, when you're multiplying and dividing, a 1 does nothing. So you don't need to write it. I literally just put nothing there besides the square root of 6. Yes, the cinematographer has cheered last one, so here we go. 1 over the 4th root of 6. This one's a little bit different. Let's talk about it. 1 over the 4th root of 6. Well, what can I multiply this by that'll get rid of all of those 4th root of 6's, all those radicals? Well, this time I need 4 of the same number multiplied times itself to get me a 6. So whatever this number is, I'm going to have 4 of it on the bottom. But if I'm going to multiply the bottom times 3 of these, I've got to multiply the top by 3 of those, right? Because once again, by the way, you'll notice the value of this fraction is indeed 1, which of course, as we've said about 100 times in this video, is nothing. So of course you can do that. Let's talk about it. I can also put all of this together if you prefer. You can think of this as the square root of 6 times, the 4th root of 6, 4th root of 6, 4th root of 6. Those are all the same radical. You could put those together. You could simply say 6, 6, 6, that's 6 to the 3rd power. And I did that top and bottom. Now, on the top, 1 times the 4th root of 6 cubed is 1 times the 4th root of 6 cubed. And notice I left out the 1 again because the 1 is nothing. If you don't know that answer by the end of this course, or the end of this chapter even, we got a serious problem here. At any rate, I want you to notice the bottom. There's 2 ways to think of this. You could almost add your exponents together. I had 1, 6 in this first radical. I have 3 in the second radical. So I could think of that as the 4th root of x to the 4th. Or I could just look back here and multiply those all together and come with exactly the same conclusion. Now, what I do need for you to see, though, is that these are opposite operations, right? 4th root, 4th power, those are opposite. They essentially cancel each other out. If you prefer, you could think of that as 4 to the power over root, but 4 over 4 is just 1, and if I have 6 to the 1 power, again, kind of 1 does nothing here. I'm just saying I literally have 1 6. So in the denominator, that's all you do is put that 1 6. And I have now, noticed, rationalized the denominator. The only radical was in the top, which is an acceptable form to leave these fractions in.